All right, so yeah, thanks everyone for having me here. Thanks to the organizers. I was a postdoc from 2013 to 2017 here, and it's fantastic to be back and see a lot of familiar faces and other people that also had time here back in the day. So I'm going to talk about today about how we measure the potential of our galaxy using streams. This is something that kind of started here, and the big surveys that we started off based on this were actually started while I was here, which is very nice to be back and talk about it. So because it's a broad audience, I want to start with a really basic primer of what streams are and like why they're useful. So this is a really toy model of how a stream looks. So you have a ball of stars. So streams form as a globular cluster or a dwarf galaxy goes around the Milky Way. So this here is a little ball of stars that I've drawn there, right there. It's going to be orbiting around the galaxy. And so what does a stream look like? Well, just like this tides from the moon on the Earth, the stars can get pulled towards the Milky Way and away from the Milky Way by tides, just like the water on the Earth is pulled towards and away from the moon. And what's different about the tides here is that they can rip the stars off. The water stays on the Earth, but here the stars can get ripped off of this bowl of stars, and once they're stripped, they basically follow the orbit that that bowl of stars, be it a globular cluster or a dwarf galaxy, was on. So they come out like this, and then you get this nice long tails forming. And these stars move along the stream. I'm going to show you a movie of that now from a simulation, but this is a toy model of how a stream looks. So now let's look at a simulation of this instead. So this is going to be a view here, just to give you that same picture. So the left view here is a globular cluster going around the Milky Way. The black stuff is stars. The dashed line is the orbit. And on the right is a camera view that follows the globular cluster on the way around. So that way the x-axis is always going to be the radial direction, and the y-axis is always the tangential direction. So kind of keeping the same view as what's over here. So we can kind of see that go around. All right, so as this ball of stars goes around, as it gets closer in, the tides rip stars off. And they come out, and then they kind of move along the orbit that it's on. And you can see on the left there that this bowl of stars is getting ripped, and that the stream is following the orbit. And that's what makes streams really, really powerful, is that when the stars get ripped off, they end up following the orbit, roughly speaking, that the bowl was on, that this globular cluster or dwarf galaxy was on. And that's what makes them really powerful, because the orbital timescales in our galaxy can be 1 billion years or many hundreds of mega years. And so streams let us see orbits in our galaxy without having to wait. So you could wait and see kind of see one star going around, but that could take a few 100 million years, or even 1 billion years. And even a small fraction of 1 billion years is too long to wait. But streams let us see that without having to wait at all. All right, so here is some data. This is the Gaia image showing some streams from the S5 survey. So the S5 survey is a survey that we started here, I think roughly in 2017. Some people in the audience are from the S5 survey as well. Vasily's in it, Geraint is in it, I'm in it. And it was a cool initiative started here, but also many other places around the world. So these are some stars from the S5 survey, and like I said, these individual dots here are stars in the Milky Way that are part of individual streams. And so they look like these kind of ribbons on the sky. So what's really cool now, like we've heard from previous talks about this great Gaia data and about spectroscopic surveys and other data sets, is that now we have phenomenal data for these streams. Actually, we have 6-dimensional data. So Gaia gives us proper motions, the angular velocities on the sky. We have S5, which is a spectroscopic survey. We've had more than 100 nights on AAT to get radial velocities, to get that line of sight velocity. And then we have variable stars for distances. So altogether, we have 6-dimensional data for all of these streams. Okay, so now I'm going to show you what we can do with this data and what we can learn from these streams. But before I show you what we can learn, I just want to say why it's interesting to learn anything from streams at all. So the dark matter halo of the Milky Way is supposed to be something like an FW halo, and it's supposed to be triaxial. So this is a plot here showing the axis ratios, C over A and B over A, so the short to long axis ratio and the mid to long axis ratio of the triaxial halo, and we're expecting it to be roughly oblate-ish for a Milky Way-like galaxy once you include baryonic effects. And on the right here, we're looking at the alignment of the halo with the disk of the galaxy. I'm expecting the halo roughly to be squashed in the same direction as the disk of our galaxy. Cosmological simulations, have these predictions. We like to test them. What's also cool is that different dark matter models also alter these predictions. So in SIDM, self-conducting dark matter, for example, this is a plot showing this axis ratio C over A to the versus the radius. Again, C over A is that shortest axis to the longest axis. So how kind of pancakey it is, roughly speaking. And in SIDM, subinactive dark matter, this ratio gets a bit more spherical. So by measuring this, we can confirm, if the predictions of CDM are correct, and we can test alternative dark matter models. And then Jason alluded to this as well, but we can also, in fact, use streams to see what the LMC is doing, and that looks a bit different in things like fuzzy dark matter. So there's lots of rich things we can learn about dark matter if we could only measure the potential of our galaxy. All right. So let me show you the data, just to show you that we have data, and then I'm going to flip over to what we can do with it. So we have the 6-dimensional data for this. I'm going to focus on one stream, which is the longest red stream. It's called the Orphan Chenab stream. So this is a kind of a complicated plot. If you haven't seen the kind of plots before. Here, the x-axis shows the angle along the stream. So this is just like the angle on the sky along the stream. And these panels show the different observables. So this is the angle across the stream, distance modulus, the two proper motions, and the radial velocity. So the point is basically that we have 6D data for the whole stream. This stretches 200 degrees on the sky and about 100 kiloparsecs across the Milky Way. We have the 6-dimensional data. And again, this is a rich data set. It's coming from Gaia, S5, and a whole bunch of other spectroscopic surveys. Okay, so that looks complicated and messy. It's hard to really see what's going on. So what can we do with 6-dimensional data? So back when we were all in school, perhaps we learned about conservation of energy, okay? So when things are far from the galaxy, they should be moving slowly. As they come in, they should move faster. So we can take this 6-dimensional data and just straight up plot distance on the x-axis, 3D distance from the center of the Milky Way, versus speed, okay? Here I've plotted kinetic energy, so this is 1/2 v squared. But what this shows is when these stars are far from the Milky Way, they're moving very slowly, and as they come in, they move faster and faster. And this color here is just the angle along the stream. So blue is the kind of trailing part of the stream, starts off over here, heads into the galaxy, speeds up, and then heads out from the galaxy and slows down. So we can see an orbit from kind of directly, and we can make this very simple measurements just to see how these stars speed up and then slow down as they head out from the galaxy. And the cool part is we don't have to wait for these orbits. We don't have to wait the billion years that this stars take to orbit the galaxy. We can just see it immediately with our data sets. And so I'm just going to show one equation, very basic, but if the stream does conserve energy, then the kinetic plus the potential will be constant. So that means that the potential is basically just minus the kinetic energy plus a constant. So we can just take this plot and just flip it over the axis to get a negative, and we get this plot here. This is just minus the kinetic energy versus radius now. And so these ellipses are data points, and this black line is what you get if you assume that the energy is conserved for the stream, which is not quite right. The kind of dashed green line is what you get if you do it correctly, and I'll explain how to do it correctly in a sec. But to within 20%, this is the potential of our galaxy. And that's nice, and I'll tell you what the mass corresponds to in a sec. Okay, the other thing that you can do with these 6-dimensional data sets is you can also ask how are the stars moving. So I said from those movies that the stars were moving along the stream. Well, once we had Gaia data, we saw that they're not moving along the stream. So these vectors here show the proper motion vectors of the stars in the stream, and they're not aligned with the stream. In fact, on the left-hand side here, they're moving upwards instead of just moving along the stream. So the stream should have been like a train of stars that the train, the velocity vectors point along the train, and it's not like that. And the culprit is right in the frame there. It's the LMC. So the LMC has flown by this stream and pulled it away from the way it should have been orbiting. And these proper motion offsets here correspond to about a 100 kilometer per second velocity kick that the LMC has imparted. So the LMC does this. And it's not just this stream. I don't have time to explain all the other streams, but most of the streams that are near the LMC in the southern hemisphere show the same effect. So this is a global thing we're seeing, and even some of the streams in the north are showing this. So it really is all over the Milky Way. So now how do we model these streams? I'll show you a movie while I talk about this. We basically eject particles in a prescription that we've tested against n-body simulations that can follow the disruption of a dwarf galaxy. So here in blue is the stream forming. The dashed line is its orbit. You see right now the kind of stream is following its orbit like in that first movie, but now you're going to see a perturber come in, which is the LMC, which flies underneath, and causes the stream to slide away from its orbit. And so this, and here are the velocity vectors in 3D in red, which show this offset. So the LMC has flown underneath the stream and basically kicked it. So it's sliding instead of orbiting around our galaxy. It's kind of like a car drifting around a corner instead of driving through the corner. So we can see these offsets, and we can easily match the kind of full data sets without any issues. All right, so what do we learn? I'm just going to flash up some things. So we get a really precise measurement of the Milky Way mass. Again, these orbits show us, these streams show us how things orbit in our galaxy. So we get a very precise measurement of the mass. This is the mass profile over here, and it matches previous measurements quite well that are made with similar types of techniques. And that precision is a 4% on the mass of the Milky Way where the stream lives. And now my favorite unit to show accelerations is in millimeters per second per year, probably because the number is order 1. So this acceleration is 1.2 millimeters per second per year where we're measuring it at, this kind of best measurement. And just because we have some exoplanet people in the room, I just want to say that's the Earth's acceleration on the sun if it were where Uranus was. So it's a very weak acceleration that we're measuring, but because the stream is a very rich data set, we can measure very tiny accelerations. And in terms of confirming CDM or not confirming, we do find that the inner and outer slopes of the halo do match predictions. We also measure the mass of the LMC. I'm going to kind of fly past this, but because the LMC has kicked the stream, we measure the mass of the LMC, and it's really massive. So it's 1.3 times 10 to the 11 solar masses, and it's comparable to a kind of 1 to the 6 ratio with the Milky Way. And we also can show that the LMC has to be extended. Because this object is hitting the stream, we can't just have a point mass LMC. We really need a very extended LMC, and this is the kind of density profile of the LMC, which goes way beyond where the stars are and confirms that it has an extended dark matter halo. So I just want to show one last thing before I talk about the final aspect, which is not only have we detected this rich data set recently, we also detected the collision point with the LMC. So this here shows the stream on the sky, and so this kind of point to the right of here is where we saw the stream before. Now we're detecting this really sharp kink. And this corresponds to where the LMC hit the stream. So this is the closest approach of the LMC, and we can easily match this. So this is the full data set now. So basically all the error bars, what I showed you before, now we have this kink. And our models can easily reproduce that kink, and we can use this to infer where the LMC was and to measure the potential even more precisely. Probably have 1 minute left, or what am I?
You don't have that.
Don't have 1 minute. Okay, so basically with these data sets, we can measure the potential of the halo very precisely. And the last part I wanted to show, but I'll say in words, is we're with these kind of data, we're even sensitive to the time dependence of the potential. Not just the LMC flying in, but even the deformations of the halo itself. So I'm going to fly over that, just showing the inference that we've had. Basically that I was a bit too ambitious here with how misaligned the disk is and the kind of deformations themselves. I'll just fly to my conclusions and then happy to take questions. So yeah, streams let us see orbits without having to wait. That's the point I want you to take away. And we can use that to measure the potential very precisely, and not just the potential, but the time dependence. And so the future of this field is what we're working on, is measuring that time dependence. So yeah, thank you for your time.
Brilliant.